Hello, I am Quentin, PhD student at the Technical University of Denmark within the Department of Civil Engineering. I am pleased to present my paper with the topic Active Mitigation of Low Temperature Cracking in Asphalt Pavements. This work was prepared with Gerald Engelmeyer, A. Levenberg and Asmus Carr, all as well from the Department of Civil Engineering. Asphalt pavements in cold regions are prone to low temperature cracking. This distress is typically manifested by transverse cracks that appear after an isolated event of fast cooling in combination with low temperature levels, or due to several cooling cycles that ultimately produce a microcrack. Due to their large lateral extent, asphalt layers are restrained from horizontally deforming. Therefore, fluctuating temperature conditions cause a buildup of thermal stresses. Specifically, low temperature cracking is induced by tensile thermal stress exceeding the layer tensile strength. Furthermore, pavement surfaces in cold regions are exposed to weather events such as snow accumulation or ice formation, or both. These hinder user safety because of the drastic decrease in skin resistance and also because of the masking of road markings. Snow plowing and de-icing operations are costly labor-intensive methods and offer slow response. An emerging solution for tackling snow and ice at the right surface of asphalt pavements is embedded electric heating in the form of ribbon elements. One advantage of electric heating technology is its ability to provide on-demand heat energy without the intervention of any truck. This work addresses the case of an electrically heated asphalt pavement with ribbon elements. It explores an unconventional application of such a system, not for combating snow and ice, but for mitigating low temperature cracking due to a single fast cooling event. The objectives of this paper are to first demonstrate that the overall idea of utilizing such embedded heating systems to deter low temperature cracking is attainable, and to second, based on the depth embedment and the output power of the heating system, determine the required time of heating activation prior to failure to mitigate low temperature cracking. To this end, computer-based calculations were carried out in which the thermal and mechanical fields were decoupled. The thermal field considered the one-dimensional heat equation applied to a half space, while the mechanical field was acquired with a three-dimensional thermoviscoelastic equation. A right-handed Cartesian coordinate system is introduced at the surface of the half space, with the z-axis pointing down into the medium. Assuming identical thermal properties and boundary conditions within any plane perpendicular to the z-axis, the one-dimensional heat equation is utilized by considering an internal heat source Q. The solution of the partial differential heat equation is acquired with a forward finite difference scheme, wherein the medium is discretized into thin sublayers of thickness 1 cm. The time is also discretized with time steps of 20 seconds each. Here represented is the model half space. The upper boundary consists of an energy balance at the surface, controlled by synthetic weather effects. In this work, the short-wave radiation, convection effects originating from the airspeed and the air temperature, as well as the long-wave radiation are considered. The wind speed is taken as constant with a value of 10 km per hour. The long-wave radiation is split between the downwelling and upwelling contributions. The considered heating system aims at representing an array of ribbons embedded at a depth of 10 cm into the medium, each ribbon being spaced 20 cm from each other, center to center. Each ribbon has a power of 40 watts per linear meter, which results in an average output power of 200 watts per square meter in the one-dimensional model. A fixed temperature of 10 degrees Celsius at a fixed depth of 1.5 meter serves as a lower boundary. The thermal analysis considers one-day periodic weather effects. Assuming cloudless sky conditions, the short-wave radiation is obtained with a combination of a heaviside step function multiplying a sinusoidal function. The short-wave radiation reaches a maximum value of 300 watts per square meter and has a non-zero value for 5 hours and 33 minutes, denoting the average duration of sunshine in a typical day. The air temperature is assumed to linearly increase during the sunshine period and linearly decrease during nighttime, reaching maximum and minimum values of -6 degrees Celsius and -14 degrees Celsius within 24 hours. The air temperature was linearly decreased with a constant rate of 0.18 degrees Celsius per hour for the two last days. This decrease aims at subsequently augmenting the thermally induced tensile stress. The downwelling long-range radiation is taken as constant with the value of 200 watts per square meter, while the upwelling long-range radiation is estimated considering the pavement surface material as behaving like a black body with an associated emissivity and applying the Stefan-Boltzmann law. The thermomechanical model represents a half space which extends to infinity in the x and y directions. With the change in temperature level, this representation does not allow any deformation within any plane perpendicular to the z-axis. Under a change of temperature delta T, this means that the half space does experience zero stress in the z direction and non-zero stresses of equal magnitude along any direction within planes perpendicular to the z-axis. The mechanical formulation aims at quantifying the thermal stress history specifically in the xy plane, where the low temperature cracking typically occurs. For this, a linear viscoelastic solid constitutive relation is selected, governed by one-dimensional relaxation modulus and a Poisson's ratio. Initially, the half space is considered completely stress-free at a reference temperature of 0 degrees Celsius. If the material is exposed to a constant temperature level above this reference, it can approach a stress-free state provided sufficient relaxation time is allowed. Conversely, if the material is exposed to a constant temperature level below this reference, induced stresses do not approach zero regardless of the amount of relaxation time allowed. This linear viscoelastic formulation utilizes the time-temperature superposition principle, assuming that the half-space material is thermologically simple. Additionally, the relaxation modulus function is taken as a 4-parameter sigmoid, and the so-called reduced times are obtained with the time-temperature shift factor, expressed in this work with the Williams-Wendell-Ferry WLF equation. The solution of the thermoviscoelastic integral equation is solved numerically utilizing the trapezoidal rule with constant time steps of 20 seconds. Based on the presented thermomechanical model, the thermal formulation was applied during 10 days to calculate the surface temperature, and then the mechanical formulation was utilized to quantify the thermally induced stress at the surface of the half space. The aforementioned air temperature decrease aims at generating thermal stress which exceeds the defined half space material tensile strength of 2.5 MPa. The presented chart displays the evolution of the surface temperature and the thermally induced stress for the 4 last days of the simulation. As can be seen, for the selected parameters of the mechanical formulation, the thermal stress exceeds 2.5 MPa at the end of the 10th day, meaning a low temperature crack would have occurred for this thermomechanical scenario. This animated chart gives a magnified view of the last 6,000 seconds of the thermal stress, with the crack occurring at an exact time of 862,790 seconds. At the time of the crack, the surface temperature reaches approximately minus 18 degrees Celsius at a cooling rate of about 0.4 degrees Celsius per hour. Next, thermomechanical calculations were repeated, this time with the heating system being activated prior to the afore identified cracking event. Once the heating was activated, it was kept on, with an output power of 200 watts per square meter. 3 required times of heating system activation were investigated: 600 seconds, 1800 seconds, and 3600 seconds. The presented chart offers a magnified view of the thermal stress for the last 6,000 seconds of the simulation for an activation timing of 600 seconds. As can be observed, the heating was not activated early enough to mitigate the cracking event, as the thermally induced stress reaches the half-space material tensile strength. With the focus set on the same time span as on the previous chart, activating the heating 1800 seconds prior to cracking is sufficient to avoid the low temperature failure. Finally, since 1800 seconds was sufficient to mitigate the cracking event, 3600 seconds are as well. During these 6000 seconds, compared to an activation timing of 1800 seconds, a timing of 3600 seconds results in a minimal thermal stress value occurring 1680 seconds earlier. The presented table aims at summarizing the obtained thermomechanical results. For no heating, the minimal thermal stress reached the defined tensile strength at a temperature of minus 17.69 degrees Celsius and at a cooling rate of 0.373 degrees Celsius per hour. For an activation time of 600 seconds, the thermal stress and the surface temperature at which the crack occurred remained the same, with the cooling rate being slightly enhanced. For 1800 seconds, the thermal stress reached a minimal value of minus 2.48 megapascal, representing 99.3% of the tensile strength. Also, the surface temperature was slightly enhanced by 0.03 degrees Celsius, while the cooling rate rose 34.3% slower. For 36,000 seconds, the thermal stress reached about 97% of the tensile strength. At the cracking time, the surface temperature was enhanced by 1.6% and was not decreasing compared to the other activation timings, but increasing at a heating rate of 0.351 degrees Celsius per hour. To conclude, the active mitigation of low temperature cracking is deemed possible. For the considered thermomechanical model, their parameters, and the critical thermal event, the heating should be activated at least 30 minutes before. Future research includes the utilization of real weather data and a layered medium which thermally represents a pavement system with from top to bottom an asphalt concrete layer, an unbound granular base layer, and a subgrade layer. Additionally, the thermal formulation will include the effects of the moisture freezing and thawing within layers. Sensitivity analysis to quantify the effects of the heating system's embedment depth and output power on the activation timing will be carried out. Also, a generic and automatic method applicable to any scenario for timely activation of the heating system is on the agenda. Finally, it is planned to implement this generic method on a full-scale test section built on the campus of the Technical University of Denmark. Thank you for the attention. Should you have any questions, I will be pleased to answer them online.